Welcome to the deep dive. Today we're getting into, well, the new physics of computational scale. When you look at modern AI infrastructure, we've just blown past the idea of server racks. We're now talking about infrastructure that needs the power of a small city. I mean, our source material lays out this just astonishing scale. A single AI data center campus, it's now projected to consume energy equivalent to an entire metropolitan area.
Yeah, we're talking about 1 gigawatt, maybe more.
1 gigawatt. And for context, that's roughly the power consumption of San Jose, California. But the mission of this deep dive isn't just to, gawk at big numbers. It's to really understand the core engineering principles that are needed to sustain this. We're focused on the twin challenges of power management and thermal control.
Exactly. And that's what makes these gigawatt-scale AI superclusters possible. It's all about the volatility of their workloads.
Right.
And that volatility, that's the key. Traditional data centers, they were running between maybe 5 and 20 megawatts. Manageable. AI facilities, they scale past 100 megawatts. Sometimes they get close to 2 gigawatts. But, and this is the important part, the size alone isn't really the problem.
It's something else.
It's the type of workload. It's a radical shift. Earlier data centers, they hosted mixed tasks, storage, web serving, all different compute jobs.
So it all sort of averaged out.
And naturally smoothed out the overall power demand. But an AI supercluster is, well, it's different. You've got hundreds of thousands of GPUs all running the exact same massive training job at the same time. Concurrently. And that synchronization that introduces these dramatic, almost instant demand swings that, traditional power systems and utility roles, for that matter, they were just never designed to handle.
Okay, let's unpack this, because the idea that having everything synchronized actually creates more chaos, not less, that seems a little counterintuitive. So where does that power volatility actually come from?
It comes from the cycle of the training itself. So during an AI training job, the system is going back and forth between these periods of intense, full-speed calculation and then these necessary administrative tasks.
Okay.
And one of the most important ones is called checkpointing. That's where the model's progress is saved across the entire distributed system.
So it's basically hitting the save button.
In a manner of speaking, yes. And when that training job hits the checkpoint, the compute load suddenly just pauses. Because the network interconnects are all busy coordinating, sending packets back and forth, writing data to storage.
And that creates a dip.
A sudden steep lull in the power demand. And then, as soon as the checkpoint is done, the load snaps instantly back up to 100% compute.
So if you have a massive cluster, a 1 gigawatt facility, and it's going from 100% load down to 30%, and then bam, right back to 100. What does that actually do to the power grid? Because I imagine the utility is not a fan.
That's the nightmare scenario for them. The sources we looked at note that these swings can jump from, say, 30% to full load in milliseconds. And utilities, they're governed by these really strict ramp rate requirements, maybe 0.5% or 1% increase per second.
So if they need to go from 0 to 100% capacity, they need to do it gradually. It might take 100 seconds just to give the generating equipment time to respond.
Precisely. If a 1 gigawatt load suddenly demands an extra 700 megawatts of power instantaneously, the utilities generators, which are these massive pieces of spinning equipment with tremendous physical inertia, they just cannot physically spin up fast enough to cover that deficit.
So what happens?
That failure to match supply to demand causes a momentary drop in the system's frequency, and that can destabilize the entire regional grid. It's a violation of physics as much as it is a violation of the utility contract.
Okay, so we have these slower multi-second swings from checkpointing, but the sources also point to an even more intense challenge on the micro level. It's called electrical design power, or EDP, sometimes just called spike power. How's that different?
The EDP spike is where the synchronization becomes truly challenging.
Yeah.
It operates on the millisecond or even microsecond scale.
So much faster.
Much faster. A rack might be designed to draw, say, 100 kilowatts continuously. But at the component level, if all the GPUs, CPUs, and accelerators in that rack all activate their highest power states at the same time, like a coordinated turbo boost,
right,
the instantaneous power draw can spike by 50%. So it might hit 150 kilowatts.
That's a huge transient spike for just one rack.
It is. But in a traditional data center, those spikes are asynchronous. They kind of cancel each other out across the facility.
Oh, okay.
What's totally unique to AI is that because hundreds of thousands of these components are running the exact same phase of the training job, these EDP spikes happen concurrently across the entire campus.
So if our 1 gigawatt facility sees that 50% concurrent EDP spike,
The theoretical demand instantly hits 1.5 gigawatts, and there is no piece of utility equipment that can react to that kind of microsecond surge.
that puts all the engineering pressure squarely on the data center then. They have to manage that internal volatility before it ever even hits the grid. So,
Oh.
what are the trade-offs? How do you tame this chaos? The sources describe a three-layered approach.
Yes, that's right. The three levels are software, hardware, so the chip itself, and then dedicated energy storage, or ESS.
Let's start with the simplest fix, layer 1, the software mechanism. What are engineers actually doing to smooth out that consumption curve?
So the goal is basically load leveling, and they do it through advanced scheduling. Instead of letting the compute drop all the way to 30% during checkpointing, the software intelligently runs background tasks.
Like a dummy workload.
It could be, but ideally it's a useful workload. It uses that suddenly available GPU capacity to run pre-processing, data preparation, maybe even other less critical training tasks. The point is to keep the aggregate GPU utilization at a steady state, say 90%, even if the main job is briefly idle.
Okay, so layer 1 tries to use the downtime constructively, but that still means you are, in essence, burning power on non-critical tasks just for grid stability. It feels a little wasteful.
It is inefficient, which is why layer 2, the chip and hardware control, is also necessary. This one addresses the utility ramp rate problem directly. The chips themselves are now being equipped with some pretty sophisticated power management firmware.
You mean the GPUs are basically regulating their own acceleration?
Exactly. The chip can be told to respect a maximum power ramp rate. So instead of jumping from 30 to 100% instantly, the chip will slowly ramp up its power draw at that mandated 0.5% per second rate. It smooths the transition internally.
And on the other side, the dip.
You can set a minimum power threshold. You can tell the chip, hey, never drop below 80 or 90% load, even during an internal lull.
But both of these controls, software and hardware, they rely on the same fundamental trade-off, right? You're either using or just burning electricity to keep the load steady. The GPU is acting like a resistor, a continuous power sink. So if you're trying to build the most efficient facility possible, that brings us to layer 3, the energy storage systems.
Right. Layer 3 ESS is really the preferred energy-efficient solution because it doesn't burn the excess electricity, it stores it.
Ah, okay.
When the load dips during a checkpoint, the ESS charges up using that momentarily surplus power. When the load spikes from an EDP event, the ESS discharges instantly to cover that demand.
So from the utility's perspective, they see a perfectly flat or maybe a gradually ramping load curve. They're completely isolated from the chaos happening inside the AI cluster.
That's the intent. An ESS deployment is itself layered, depending on the duration of the volatility you're trying to fix. For those extremely fast sub-second EDP spikes, you deploy supercapacitor shelves right there in the rack.
Why supercapacitors?
They just handle that rapid high cycle charge and discharge better than chemical batteries. Then you have two longer duration layers. A large-scale campus ESS for minutes-long grid stability, and crucially, the enhanced UPS.
We should probably clarify why an enhanced UPS is required. I mean, every data center has a UPS. What makes this version so different?
It all comes down to the duty cycle. A traditional lead-acid UPS battery is high capacity, but it's low cycle. It's designed for one thing, hold the load for a few minutes, maybe once a month, while the generators spin up.
That's it.
It absolutely cannot handle hundreds of thousands of rapid charge and discharge cycles happening every few milliseconds. That's what you need to smooth AI workload volatility.
So the enhanced UPS needs a totally different battery chemistry, often lithium variants, that's designed for these high life cycle rates. So it can cycle power really fast without degrading immediately. It becomes an active power management component, not just a passive backup.
Precisely. And this is the moment where the traditional role of the UPS is just completely inverted. We're all used to thinking of the UPS as protecting the expensive IT equipment from the instability of the external grid.
But now, because these campuses are gigawatt scale, the enhanced UPS is protecting the external grid from the sudden synchronized chaos that's happening inside the data center. That is a total reversal of responsibility.
It is the very definition of acting as a good grid citizen.
Yeah.
If your data center campus is 10% of the regional power load, the utility needs you to be a stabilizer, not a source of potential disaster. which brings us directly to the concept of low voltage ride-through, or LVRT.
Right. And what happens when a 1 gigawatt facility acts correctly, in the old sense of the word, when there's a regional power problem?
So imagine there's a fault on a transmission line. A lightning strike? Maybe. It causes a temporary voltage sag down to 50%. A traditional UPS sees this threat and instantly does its job. It takes its massive 1 gigawatt load off the utility and switches to its batteries to protect the IT gear.
Which is what it's supposed to do.
Right. But now, scale that up. If 5 or 6 major data centers in a dense region like Silicon Valley or Northern Virginia all do this at the same time, you got 5 or 6 gigawatts of load that instantly drops off the grid.
Oh, wow.
And this massive sudden load withdrawal causes an immediate dangerous frequency spike on the utility side.
And that frequency spike can trip safety mechanisms at the power plants, which causes a deadly cascade. So the very act of protecting the data centers could result in a widespread, chaotic, rolling blackout for everyone else.
That's the chain reaction the utility has to prevent.
Yeah.
So the LVRT requirement mandates that the data center must maintain consumption during a sag. They use the enhanced UPS not to take the full load off the grid, but just to supplement the voltage deficit until the utility stabilizes the line.
And what's the timing on that? Because transmission faults are often fixed almost instantly.
That's the critical detail.
Yeah.
Once the voltage stabilizes, which might only take hundreds of milliseconds, the enhanced UPS has to be able to put the full gigawatt load back onto the utility within 1 second. It has to reintroduce that load gradually, precisely, so the utility's generators don't see another massive sudden shock. It transforms the UPS into this micro-stabilization engine for regional power.
So the power side is solved with dynamic energy storage and chip control. But this 1.5 gigawatts of synchronized power draw is generating a monumental amount of heat.
Let's pivot from the gigawatt power problem to the gigawatt heat problem, because air cooling has just fundamentally hit its limit, hasn't it?
Absolutely. The density of modern AI compute means air cooling is, well, it's obsolete. Engineers are constrained by the volumetric heat capacity of air, which limits effective cooling to about 30 kilowatts per rack.
And we're way past that.
Oh, yeah.
Current GPU racks are 100 kilowatts. Future roadmaps are targeting 500 kilowatt or even 1 megawatt racks. So liquid cooling isn't an option, it's a prerequisite.
And this isn't just, dumping cold water onto the chips. The sources detail a really sophisticated two-loop architecture. It's about reliability and efficiency.
That's right. It relies on 2 segregated closed-loop systems. We start with the inner loop, called the TCS, or Technology Cooling System Loop. This is the highest purity loop.
Why does it need to be so pure?
Because this fluid, it's often highly filtered water with an antibacterial agent, it flows directly through the cold plates. Now, these are custom machined metal blocks with microscopic channels that sit right on top of the GPUs. If you have any mineral deposits, any impurities at all in that water, you risk clogging those microchannels.
And that's catastrophic.
Immediate catastrophic chip failure. So the TCS absorbs the heat from the chips.
And that hot fluid then goes where?
It goes to the most critical component, which is the coolant distribution unit, or CDU. The CDU is basically a massive industrial-grade heat exchanger. It manages the heat transfer from that inner TCS loop to the outer loop, which is the facility water loop. The facility loop is your external chilled water. It operates at a lower purity and much higher volume, and it carries the heat away from the CDU to the exterior of the building. By keeping the TCS and facility loops separate, you ensure those sensitive chip cold plates never risk contamination.
That distinction really clarifies the engineering challenge, but the final, and maybe the most important design constraint here, especially given the environmental focus today, is this mandate of zero-net water consumption. How do you dump all that heat without evaporating millions of gallons of water?
That single requirement just changes the economics of the entire cooling solution. I mean, traditional evaporative cooling towers, they're cheap and they're effective, but they consume massive amounts of water through evaporation. They're not viable for a city-scale load in many parts of the world.
So what's the alternative?
To get to zero-net water consumption, both the inner TCS and the outer facility water loops, they have to be 100% closed systems. The heat is ultimately rejected using what are called dry coolers.
Which are fundamentally just massive car radiators, right?
Essentially, yes.
Mm-hmm.
Just scaled up dramatically. They are coils that the hot facility water flows through, and then these massive fans blow ambient air across those coils, rejecting the heat to the atmosphere without any water-to-air evaporation. They might be a little less efficient on the very hottest days compared to evaporative coolers, but they conserve every single drop of water. They stick to that zero net mandate.
This has been a fascinating look at the incredible synthesis of power management and thermal engineering that makes modern AI actually function. Let's just quickly distill the major takeaways for you. First, AI compute is really defined by synchronous volatility. The sheer scale and the concurrent operation of those EDP spikes and the checkpointing dips, they demand dynamic management solutions that stabilize power way faster than any traditional system. Second, teaming this chaos, it takes a multi-layered approach that has to prioritize efficiency. So the use of these highly responsive energy storage systems, which store and redeploy power instead of just wasting it through chip-level smoothing, that's becoming essential.
Absolutely.
Third, because of their gigawatt size, data centers have to become good grid citizens. And that means implementing enhanced UPS systems with low-voltage ride-through capabilities. This allows the campus to act as a microstabilizer, preventing these mass synchronized load drops that could otherwise trigger widespread blackouts. And finally, the thermal wall. It just requires sophisticated high-density liquid cooling. This is achieved through two fully closed loops, the high-purity TCS loop and the facility loop exchanging heat through the CDU, and then rejecting that heat entirely using dry coolers to ensure zero net water consumption.
And if we connect all this back to the broader picture, the engineering here, it really shows that these gigawatt campuses are not just big customers of the grid anymore. They are highly integrated utility-scale infrastructure in their own right. They are stabilizing regional power and managing water usage on a scale we've just never seen before.
It's a fundamental shift.
It is, and this raises an important question.
Yeah.
If these AI facilities are now required to support LVRT regulations to protect the power grid, and they're rewriting environmental rules with zero net water mandates, how will things like city planning, infrastructure permitting, and land management rules, how will they need to fundamentally adapt as these hyperdense, high-impact digital cities become the norm? It's a complete inversion of how we categorize utility customers, and it's something worth exploring further.
Absolutely. Thank you for joining us for this deep dive into the silent, complex engine of modern AI.